Alright, so we've talked about how electrical charges could be used to cause electric motors, which are very useful things and run a lot of things around our homes. But let's look at something even more basic because, first of all, if we're going to run an electric motor around the home, we have to plug it in and get electricity. So where does electricity come from? Let's look at how that developed. In the 1860s, there were two men. Michael Faraday was in England, and Joseph Henry was in the United States. Okay, and as often happens in science, they were both studying the same type of thing, and basically they were studying the connection between electricity. Sorry, here we go. Let me write this down real quick. Okay, Joseph Henry, and they published about the same time, and so they both kind of gave equal credit for this. I'm sure if you're in England, Faraday gets more credit, and here in the United States, Henry. But basically, they both gave credit that electricity could be produced by using magnetism. Up until this point, the only time we have electricity was if you had batteries. Okay, and we were familiar, of course, with the idea of batteries. Batteries use direct current, stored up energy based on chemical reactions going inside of it, and they only use direct current. But the problem is batteries could not store large enough voltages and so forth to do a whole lot with, to be powerfully useful. Okay, they could, run small small things, and the batteries they had then weren't even that strong. In order to be useful, you need to have larger amounts of voltages and currents and so forth of electricity to do things with. And so it wasn't really considered much more than a curiosity at that point. But when they discovered that it could be used from magnetism, this was a big thing, okay? And basically what they said is that you could induce or cause voltage when you have a wire in a magnetic field. If one of them moves compared to the other one, then it will create voltage. Okay, and this is called electromagnetic induction. Okay, and so Joseph Henry and Michael Faraday both discovered almost simultaneous electromagnetic induction. Okay, there's that word induction. Just like you can induce electric charge if you have one object with charge, now we can use a magnet to induce electricity, or electricity to induce a magnet. All right, and basically, if you have these coil of wires and you move the magnet through that, okay, and if you have these wires hooked up to a meter so that you can measure electricity, you will notice that there's electricity flowing through here, okay, and if you move it this direction, it will flow one direction. If you move it the other direction, it will move in the opposite direction because you're changing the direction of the current. So it's kind of like a negative flow or positive flow. It doesn't really matter. Just like an alternating current, you've got current going back and forth. It's still a flow of electricity. And so basically you're inducing a current, even though this wire is not hooked up to a battery or anything else, no power source. By moving the magnet in these coils, it will induce a current. Okay, and there are a lot of flashlights, for example. Some have a handle so that you spin magnets in between coils, or you spin coils between a magnet, and it creates a current, and therefore your light bulb will work. So you don't need batteries, you just have to crank it. Of course, you may have to keep cranking it as you're going through the woods, but there you go. Others are what we call shake flashlights, and we'll look at one of those. You shake it up and down, the batteries, and basically you have a bunch of coils set up there, and the magnet is sliding back and forth between those coils, and it creates a current. And usually both of these kind of flashlights would have some type of battery that would hold electricity so that you could charge it up, so to speak, and then hopefully use it for a length of time without having to constantly be shaking it or to spinning the handle around. There we go. What do you call that? Okay, to keep up your current. So they hopefully have some kind of battery. Most of them are not always the greatest in the world, but they will work, and they don't have to worry about having a battery at all times that's been charged up. Okay, because these will charge themselves up if you either shake them or crank the handle enough times. There we go. Crank, the word I was looking for. All right, and so basically, I said it doesn't really matter which you do, what you move. he said, okay, for example, in this case, you could move the magnet up and down, which causes a changing magnetic field, which would cause a current to go through. Or you could hold the magnet still and move the wire up and down. Either way, it's going to create a current. Okay, so if you move either the magnetic field or if you move the coil of wire, then you're going to create electromagnetic induction. So I could hold this magnet still, but move the coil up and down, and it would also induce a current. Okay, and that's electromagnetic induction. Now, Faraday's one, I don't know why he's the first one to really formalize it, but Faraday's law, he got his name on the law. Okay, Faraday's law basically says that the voltage that you get in this coil, the voltage produced is directly proportional to two things. Okay, so it depends on two things. The more you have of one, the more you're going to have of the voltage. Okay, basically the number of coils. If you have 1, 2, 3, 4 coils here, then you're going to get a certain amount of voltage when you move this magnet through there. If you had 8 coils, you would get twice as much electricity. Okay, twice as much voltage because you have more loops. Okay, if you have 4 times as many, you get 4 times as much, and so forth. Okay, now someone says, well, then we know just more and more loops is good, and it is good, but you are going to have to, as electric current goes through these wires, they create a magnetic field. Okay, and therefore it's harder to push the magnet the more and more things you have. And that's why if you go to power plants, which are basically the same thing, they're either moving a magnet through a coil or moving a coil around magnets. Either way, it takes a lot of force because they're trying to make mega kilowatts of electricity, great amounts of electricity. So they have extremely large magnets, extremely large coils, and there's a lot of resistance as this current goes through here. It creates a magnetic field in the opposite direction, and it makes it even harder. And that's why it takes so much power to turn it. And basically, all power plants are just steam production. That's really what they do. Whether it be nuclear power plant, whether they be coal, oil or gas power plants, it doesn't really matter. They're basically burning something or using some kind of fuel to create heat to make steam, and then they use steam, basically a steam engine, if you will, and they're using that to turn either the magnets or the coils to create electricity. But that's why it takes such a great amount, because you're getting this resistance. As more electricity moves to the coil, then you also get a magnetic field that pushes back against your magnet that you're moving through there. And so really that's basically, the only ones that don't really use steam would be like a hydroelectric, where they're using the force of gravity pulling water through. But that's also a very great force, and it uses it to turn those around. Okay. Now, the other thing is, besides the number of loops, is that you can, it's also how fast do you move the magnet back and forth. Okay, the faster you move the magnet back and forth, then you're going to, the rate at which it changes, that's also going to create more of a current here. So the number of loops and how fast you move the magnet back and forth. Okay, and also the strength of the magnet, although we haven't put that, that's not actually part of his law, but the thing is, now, when does this happen? A lot of times, stoplights, when you go to stoplights and there's not a camera or anything that monitors it and tells it when to change, a lot of times there's a piece of iron underneath, with a magnet underneath, and a magnet put underneath the road, and as you drive over it in the turning lane, the iron or the metal of your car induces a current, and that sends a signal up to the thing that says, yes, you have a car there. Okay, basically when you go through a metal detector, if you have metal on you, it influences the coils that are in the both sides of the little metal detector, and it begins to conduct an electric current as the metal moves through, and so it sets off an alarm saying, yes, you have metal on you. Even on your credit cards, debit cards, things like that, any cards that are swiped without a chip, but if they're swiped, there are little magnetic fields in there and on the loop, and so as it goes through coils in the reader, it can read the different magnetic fields and get your information off of it and know how to charge it and so forth. So electromagnetic induction is something that occurs in many, many ways, but probably the biggest way is power plants. Okay, all of our electricity ultimately comes from a power plant. Even our battery things, we usually have to recharge them. We have much better rechargeable batteries for our phones and so forth, but we have to plug them in and do that. So we've talked about motors, electric motors. Now they're dependent upon magnets, using an electromagnet and a wire armature to spin, and then it alternates the current. It repels, attracts, this little thing called it spin, spin, spin. All right, and that creates mechanical energy. Okay, that is a motor. So in a motor, you put in electricity, and it outputs some type of mechanical action. Now, it's possible to do just the opposite. If you turn the armature inside this electromagnetic field, as it turns, it's going to change the magnetic field. It's just like moving a coil of wire basically through an electromagnetic field, which is going to induce a current. And so if you turn this mechanically inside the electromagnet, this loop of wire, it will create an electric current coming out on the other side. And that is basically, in effect, what a generator is. All right. And kind of what we talked about with electromagnetic induction. Okay, if you're moving the coil within a magnetic field, then it's going to create electricity. All right. Here, for example, is a small electric motor. Okay, if we use steam or something to turn the electromagnetics and coil of wires inside of here, instead of putting electricity in to get in motion, like spinning a propeller or something like that, we can spin the propeller with steam or wind or whatever, or by hand, and it will turn the electric thing in here and create electricity. So basically, the difference between a motor and a generator, you're putting in mechanical energy, some kind of kinetic energy, causing the electromagnetics or the coil wire to move, and you're creating electricity. With an electric motor, you're taking electricity and causing something to move. So they're just kind of the inverse of each other, the opposite in a sense of how they work. All right. Besides things like this, obviously power plants would use this. Basically, you have steam that turns big turbines, which turns the magnets inside an electrical field, and that creates electricity. It can also do, though, for example, hybrid cars, when they're accelerating or climbing, they take current from the battery because they need extra current to help the motor get up. And so basically, it's acting like a motor. It's taking electricity from the battery and using it to make mechanical energy and help it up the hill or as it's trying to speed up. However, if you're braking or coasting, all right, it actually uses the energy from braking, or as it's coasting and it's turning around, it allows that turning motion of the wheels to help turn basically like a generator, and it's sending electricity back into the battery. So it's kind of a hybrid car actually has a hybrid. The battery is acting kind of like a battery or motor in that it gives electricity to cause motion, but it also uses the motion of the wheels when you don't need that little extra boost from it to act as a generator, and it turns and it sends electricity back to the battery and stores it in the battery. So it works both ways. All right. Now, once again, a generator does not just generate energy out of nothing. It can only take mechanical energy and change it back into electrical. All right. Now, we can understand how if there's electricity, if a wire is moved in a magnetic field, it creates electrical field, and if we have electrical field moving in a magnet, electrical charges moving through a wire, it can create magnetic field. But it turns out that Faraday's law can also be considered true even if there is no wire present. If you just have electric charges in space, as they move, they will create a magnetic field. Or, excuse me, if there's a charge moving in space, it would create a magnetic field. If there's a magnetic field moving through space, it will create an electric field or induce an electric field. Okay, and so the same thing would be true in outer space. And it so turns out that a certain class of energy known as electromagnetic waves, because they're both electric and magnetic, are formed when you have a magnetic field changing, causes a magnetic field change, and this can be passed throughout space, and this is called electromagnetic radiation or electric electromagnetic waves, and these would be things like light, radio waves, X-rays, gamma rays, UV, infrared, microwaves, and so forth, and we'll talk more about those later. These all travel at exactly the speed of light because it's very efficient, and we're going to stop right there.